Hello everyone, I'm Florian Hofherr and I'm happy to present our work on neural implicit representations for physical parameter inference from a single video. We are interested in planar physical phenomena like the pendulum shown here. We aim to jointly estimate the physical parameters and to reconstruct the scene appearance. As input, we are given a single video taken by a static camera. Our method works on a per-scene basis. We assume that we can describe the physical phenomenon by a parametric model, for instance by an ordinary differential equation. We are interested in estimating the physical parameters of this dynamics model. For the example of the pendulum, these parameters would be the location of the hinging point, the length and the damping coefficient of the pendulum, as well as the initial angle and initial angular velocity. Moreover, we are interested in obtaining a representation of the scene itself. That allows us to render the scene under novel physical conditions, for example, with changed damping. Our method eliminates the need for large amounts of training data from several of the previous methods. In comparison to other methods that also work on a per-scene basis, we achieve physically more realistic results. We perform the reconstruction in an analysis by synthesis manner. First, we use a coordinate-based representation to model the background. A learnable MLP maps locations to colors. To model the dynamic object, we use another MLP that we place on top of the background. This representation yields opacity besides the color to allow for arbitrary object shapes. We use a time-dependent transformation to position the dynamic object in the scene. The first part of this transformation is an affine mapping that is parametrized by the solution of an ODE. This is the ODE that encodes the physical phenomenon and is itself parametrized by the physical parameters that we want to estimate. Since the image plane and the plane in which the dynamics are happening do not need to be parallel, we add a learnable homography to the transformation. To render the color at a pixel X, we evaluate both the background representation and the representation of the object, where we use the transformation to obtain the pixel position in the local frame. Both representations yield a color, and we use the opacity from the local representation to blend those colors together. Since the transformation is time-dependent, we can render the scene at different time steps. We use a simple mean squared term on the photometric error as our supervision loss. Our method is able to create a realistic reconstruction of synthetically created pendulum scenes with different appearances and varying physical parameters. One previous approach to add dynamics to coordinate-based representations is to make the representation time-dependent. For sparse observations in time, this results in a visible blending between the observations rather than the realistic motion shown by our method. Also, since the extrapolation in time is not supervised, predictions in the future are not possible. In contrast, our method is able to predict the physical behavior with high accuracy. Besides the synthetic examples, we also consider three real-world scenarios: a sliding block, a thrown ball, and a real-world pendulum. Our method also allows to render the scene with changed physical parameters. For example, we can increase the damping for the pendulum. Or we can change the initial position and velocity of the ball to throw multiple balls through the scene. Thank you for watching.